Good morning, everyone. My name is Kaushal Kumar Singh, and I am the lead blockchain developer. So today, I'm going to start with the overview of the Zond, a brief presentation which will give you an idea of what we are working on and what we have achieved so far now. So let me share you my screen. Okay, so this is the Zond overview. So we will begin with our types of wallet. So in Zond, we have XMSS and dilithium, two types of wallet. So basically, these two are different types of post-quantum cryptography that we have used. And coming up with the difference is like in our Zond node, when you generate an XMSS wallet, you will see the address starts with 0x1, as I have already mentioned here. And XMS is a stateful signature scheme. So that means every time you make a transaction on the blockchain side, we have to uh, make an update related to your private key that, okay, this specific OTS index and private key has already been used. So that's what the stateful signature scheme is. So XMSS is a stateful signature scheme. So with the stateful signature scheme, there comes something like that even user has to take care of, which is you have to keep track of your OTS index just to make sure that you do not reuse it. Otherwise, if you sign a transaction with an already used OTS index, that will be uh, rejected by the blockchain itself. But the problem is because you broadcast your transaction and you are reusing your OTS index, that will compromise your wallet security to some extent. And because it's a stateful signature scheme, so XMSS has a limitation of like there is a limited number of secret keys. That means you will reach eventually to a point where you can end up with having no secret keys unless you are using the slave feature, which we are still implementing on the Zond node. It's not yet implemented, but for our Python node, which is still working on proof of work, the slave feature is still there, and exchanges are using that, and they have like virtually unlimited secret keys. So that's still in progress for the Zond node. On the other hand, we have dilithium. So basically, a dilithium wallet, it's a stateless signature scheme, and the address usually starts with 0x2. Already mentioned one of the example address here. So it's stateless. That means user doesn't have to keep track of anything, and neither blockchain has to update any kind of secret key or anything like OTS used or not. So it's simple in terms of development for us, and in terms of for users to uh, maintain it, the dilithium one. And that's because it doesn't have any stateful signature scheme. So it's like you can have unlimited number of transactions using dilithium wallet. So that's the difference between XMSS and dilithium. So further differences with the signature size. In XMSS, we have a base signature size of like 2180 bytes, and then it depends upon height. So if in an XMSS tree you have a wallet of height 10, that will make it around 2500 bytes signature size. But the public key size is fixed to 67 bytes. Whereas in dilithium, the signature size is fixed to 2687 bytes, and public key size is fixed to 1472 bytes. But yeah, these sizes are very big for the blockchain, and it's like a transaction going to have at least, if you take the sum of signature and public key, then at least that much size will be the minimum size of the transaction just to cover up transaction public key of dilithium wallet. And that's how it goes for XMSs. Now in terms of feature, so right now in Zond node, if you use XMSS wallet, you will be able to transfer funds, the testnet funds or the Devnet funds, from one wallet to another. It's fine. You can transfer your funds from XMSS wallet to a dilithium wallet or XMSS to XMSS wallet. No issues with that. You can also deploy smart contracts, interact with the smart contracts, but staking is not yet allowed. We are making progress with to make XMS available for staking. But if you use dilithium on the devnet, you will have all the features including staking, interacting with the smart contracts, deploying smart contracts, transfer of funds, everything will work without any issue. uh, okay, so now coming to the API. So in Zond node, we have got two kinds of APIs. One is the public API, which is basically the legacy API, which we wrote around like 2 years ago. But that's deprecated right now. It's like it's still there because it has some dependency on Zond CLI, uh, because Zone CLI is using the legacy public API, so we haven't removed it yet. But in the upcoming updates, we are going to remove this public API, and Zond API and the Zond CLI will be using RPC API instead of the public API. Right now, the public API default port is 15005, and the second API, which I am going to talk about, is the RPC API, which we have implemented, and it's very much similar to Ethereum's RPC API. So right now it supports only HTTP protocol, and we are working on some of the APIs like event subscription API. So there's a bunch of APIs that are in progress in the RPC APIs, but we have already implemented many of them. Especially the subscription event subscription API is still in progress, so that would take some time. But in the upcoming upgrades, we will have that too. So the RPC API, as I mentioned, it's only support HTTP protocol, but we are working to make it to add like the WebSocket and IPC protocol implementation for this. And the default port for this RPC API on Zond node is 4545. Now, getting to our proof of stake consensus mechanism. So before I move like how this works, I would like to go through the terminology that we use. So in proof of stake, we call anyone who is participating as a staker a validator. So basically, anyone who has a stake balance greater than equal to 10,000 QRL, they are considered as validators. This 10,000 QRL is the minimum amount required if you want to become the validator and stake on the node, but this is not something fixed yet. When we will release the mainnet, this value may change. So when we come to the validators, there are basically two types of validators, or I would say like there are role of validators. So there are basically two kinds of role. One is block proposer, other is attesters. So block proposer, mentor, slot leader, these are like the same thing, but they have a different name. So it basically represent to the same thing. A block proposer, who creates the block. Mentor is the same thing. Slot leader is the same thing. Attester is the something different. So we will talk about what's the difference between block proposer and attesters. Now the block proposer is the one who creates the block and add transactions into the block. So that's what the block proposer responsibility is. Whereas the attester's responsibility is to get the block which was created by the block proposer, then it basically signs the attester transaction on it, which basically means that it is vouching for the block as a valid main chain block. So if an attester sees a block coming from a valid block proposer, it makes sure that this block belongs to the main chain that he thinks based on whatever state that it has on its node, and then it signs the attester transaction, gives back it to the block proposer. Block proposer then collects all those transactions, add it into the blocks so that it has sufficient proof by the attesters. So that's what the role of attester. Attesters just gives a vote on the block, whereas the block proposer just creates the block, add transactions into it. Now, coming to this, like how is this role is assigned on our side. So we have a very naive random function at this moment. We are still working to improve our random function. So whenever an epoch starts, this role is randomly assigned to the validators. So if there is a list of validators, and if it's the first block of the epoch, so before the first block is created, the system randomly assigns or I should say, the randomly shuffles everything, and then it assigns the role. Okay, this address, dilithium address or address will be a block proposer or attester. So that's how it works. So if you are a validator in a specific epoch, so your participation will be only once per epoch, which means you can either be a block proposer or an attester, and your participation as either a block proposer or an attester will only be once per epoch. So you do not have to make any transaction after an epoch. if you have already made one of them. So the epoch size, we have 100 blocks in an epoch, which means it's like after every 100 blocks, we regenerate the list of validators, we reassign the role of all of the validators, whether they will be a block proposer or an attesters. So it's like how we do that. So the thing is, we take all the list of validators from previous epoch, and then we start adding or removing the existing validators based on whatever stake transaction they made in the blocks of previous epoch. So if someone has made a D-stake transaction in the previous epoch, it will be taken, and then that validator will be removed from the validator list. Or if someone made a stake transaction to join the validators list, then that is processed before the beginning of the epoch. And then at the final, we check like if the existing validators have at least 10,000 QRL on its stake balance. If they do not, then we remove that. If they have, they continue as a validator to the next epoch too, unless they have made a D-stake transaction in the previous epoch. So as discussed previously, this assignment of the role of whether they are block proposer or attester, it happens randomly once we have generated the list of validators. Now, the thing is, there are very, I should say, a question that comes in the mind. What happens if someone stake with more than 10,000 QRL? So, if someone using more than 10,000 QRL for staking, it will not have any impact in terms of reward or priority or anything like that. They will be still treated as if they have just have a 10,000 QRL as stake balance. However, this extra amount can help you from getting your balance below 10,000 QRL. Is like in case there will be any penalty, like you may have a chance where you have to create the block, but for some reason your node lost the internet connection, and because of that you have been charged some kind of penalty. So those penalty can take your balance below 10,000 QRL. And so for that reason, it's good to have a little bit more than 10,000 QRL so that you can cover those penalties. So that's the only advantage that you can have if you use more than 10,000 QRL as the stake balance. Now, talking about the proof of stake reward. So the reward function right now works is like all the transaction fee in a specific block goes to the block proposer, and there is a fixed reward of 5 QRL for the block proposer, whereas a tester only receives a fixed reward of 2 QRL. So if in a block there are two attesters, then each attesters will receive 2 QRL, 2 QRL as the reward. And this is just what we have got in our first iteration, but this is more likely to be changed and before we release the mainnet. But that's what it is for now. Okay, so at the end, this is our RPC API's IP and the port, the Devnet that we are running at this moment, and this is the documentation link. So if you would like to go through the APIs, how it works, so you can look into the documentation. So now I will begin with the demonstration, like how you can clone the node, run a node, and then how you can generate the wallet, how you can deploy the smart contract, interact with it. So let's begin with it. So we have a repository here. Okay, this is the Zond repository. We do not have any version release at this moment because it's like the first iteration. We will have that in future, the package manager and version things. So for now, you have to clone this repository if you would like to run the Zond node. So we have got the Zond node. I'm using Ubuntu. It's the Ubuntu terminal. So I have just cloned the Zond node. Right now, I just need to build. Okay, so that's how we build the Zond. You need a Golang version. I think the minimum required version is 1.16. And once you have cloned the repositories, then you have to just build this. So we have Zond, which is basically it will run the node. So if I write that, it's going to run the node. That's how the node starts, and then it will start syncing from the devnet, which is running on our server. So it will take time to sync. It's like we are 10,000 blocks behind. So I'm not going to wait here for it to sync. Already shown you how you can start that. So I'm going to interrupt this at this moment. Now that's the Zond node, but if you would like to use the Zond CLI, you have to build this again.
Is that connected or over?
So this is Zond CLI. That's how it looks like. And we have commands to generate wallet, transaction, dilithium keys, everything. So if you want to generate a wallet, you can use this like Zond CLI wallet. Now this will give you two options, like which type of wallet you would like to generate, whether it's XMSS or dilithium. So I'm going to say it should be a dilithium wallet. So as we have discussed previously, dilithium wallet starts with 0x2. So that's our dilithium address. We have generated a wallet. And if you'd like to have a list, then you can use wallet list. This will give you the list of wallets. So right now we just added one wallet. So that's what it is showing. If we add XMSS, this will generate XMSS wallet. It takes more time to generate. So okay, it starts with 0x1. So that's our XMSS wallet. Clear this. So if we do this wallet list, we can see our dilithium wallet that we added previously, and that's the XMSS wallet. If you would like to see its secret key, then you can use wallet secret. It will give you the hex seed. That's the hex seed, and that's your mnemonic keyword. So that's how you can play with the wallet. There are further documentation. You can take a look into that in case you want to know more about how the Zond CLI works. So that's the Zond node, and Zond CLI already covered. So now I will move to this smart contract thing, like how you can start building on a Zond node, how you can write your own smart contract, deploy it on the network, and then how you can interact with it. So for this, uh, we have created a sample code, which is Zond contract example. Uh, you have to clone that. It is how it looks like. It's the QRL Zond contract example. Uh, okay, we have cloned this repository, and we have to make this npm install. Okay, meanwhile it's working, I'm going to go through the code. So I'm using WebStorm on my side. Usually people use VS Code, so it should not make any difference. So if you are using any ID, that should be fine. All right, so npm install did work, and I have to open this repository first. Okay, this is the example repository which we have cloned. Touch this project, this window. So let me go through the structure. This is the contracts directory. So for now, for the simplicity, we assume that whatever contract that you are writing, you should copy this inside this contracts directory. And
Could you blow it up a little bit, Kaushal? Are you able to?
okay, you want me to increase the text size?
Yeah, yes, please. Thank you. I didn't know if you could hear us.
Okay, all right, let me try.
Thanks for my mistake. I think
Is that fine?
yeah, it's perfect. Thank you.
Okay, great. So This is the contracts directory. So in this example, we have already written an example contract, which is an ERC20 token. In case you are writing your own contract and would like to deploy that on Zond blockchain, initially, I will suggest you that you copy all your contract files, whatever you have written in this directory. So let me go through the example contract that we have written. So basically, this is okay. I have to read this size too. Okay, fine. So this is the example contract that we have created. It's my token, that's the contract name, and it is inheriting from the parent contract, which is ERC20. Uh, this is the source code of the ERC20, which is basically the standard ERC20 token functions. So it has mint, burn, approve, transfer. So anyone who is already familiar with the ERC20 or Solidity, they know what is this. So I will not uh, I will not go to explain these things. So, and we have a interface which is IRC20. So this basically has the functions names are like signature, the definition of the functions, but it doesn't have the actual code. So this ERC20 is implementing that specific interface. So that's the structure of our example contract that we have created. And so let's say if you have written your own contract and you have copied the CS, so the next thing is you have to do some configuration in this JavaScript file to make sure that it reads your contract. So we have a contract compiler.js. What it does, it basically use the Solidity compiler, and then it compiles your contract code and then gets the bytecode and the ABI codes which is required for to use the Web3 APIs and to interact with the contracts. So let me go through the basics of how this contract compiler.js works. So we have a function get compiler output, which basically use Solidity compiler and it takes the input. So the input should be your uh, main contract, which you actually looking to deploy. In our case, my token.sol is the main contract that I will be actually trying to deploy on the network. So what I do is in this input variable, I have to write my file name here, my token.sol, and then I have to uh, make all its content available in this specific format. Why this we require this format is just because the Solidity compiler is actually requires input in this format. So the format is like your language should be Solidity, sources should be your main contract, not the contracts that you are trying to import. For example, in my token.sol, I'm trying to import ERC20.sol. So that's not you are going to mention into input. It should be your main contract, which is my token.sol. And it's just reading the content of the file and having it here. Now the settings, I'm going to keep it like as it is. It's the default settings, but if you would like to play with the settings, you want some kind of optimizations, then you can play with that. But for now, for the sake of simplicity, I'm going to keep it as it is. So that's the first parameter required by the Solidity compiler. The second parameter is import. So if you are writing a contract which is importing something, for example, my main contract is importing ERC20.sol, then you have to provide the function which will help you to resolve these imports. But if your contract is not importing anything, you don't need to pass this parameter. You can simply delete this one. But in our case, what we are trying to cover everything so that in case someone is importing, he should not have any issue working with this. So in our example, we have made imports ERC20.sol, and if you look into the ERC20.sol, it is importing IERC20.sol, which is basically the interface. So all these imports has to be mentioned in this find imports function. Okay, this is basically the function required by Solidity compiler to resolve all the contents of the contracts which are being imported. So you just need to mention all these import name. So if you have mentioned ERC20.sol in import, you have to mention this in here, and then the path from where the contents can be loaded. And if you are already familiar with JavaScript, you know what the fs read file sync basically reads the content of the file. So that's what we are doing here. So that's the basic configuration that you have to do before you can start deploying the contract and making calls or interacting with the contracts. So once we have done this configuration, the next thing is we would like to deploy our contract. So this is one hyphen deploy.js. This is the code which is used to deploy the smart contract. So for this, you need a dilithium wallet. Uh, you can have XMSS wallet, but right now we do not have XMSS wallet support in JavaScript. We are still working on that. So in JavaScript, we only have dilithium support at this moment. So you have to have an hex seed of a dilithium wallet which have some funds, the testnet funds. In case you do not have, you can ask from the team. They can give you the testnet funds to play with. uh, we need these funds to deploy the contract, which will require some of the gas fee, and that requires to be covered by the dilithium wallet which you are using. So this is the hex seed. This hex seed right now doesn't have any fund. So if you try to run this from the console, it's going to show you the error. So it's .js. So if I try to run this, should show me error that it doesn't have funds. Okay, that's the error we have got, is transfer failed because we have insufficient balance. That's the transaction hash. uh, that's the dilithium address for the hex seed that we have used. Required balance is this much, but available balance is 0. So make sure that whatever dilithium wallet you are using, it should have enough fund. So once you update this, so let me update this with the wallet that have the funds. Okay. So I have updated this with the hex seed of my wallet having funds on it. So when you call this deploy function, it takes the address, your dilithium address, because you are going to deploy the smart contract using your dilithium address. So that requires your address. Second thing, we need the compiler output, the configuration that we made previously here in this get compiler output everything. So we call this function here get compiler output. So in this output, we get two important things. So the first one is the EBI file, which is the binary interface. It is required, this application binary interface data is required to make calls. So, and that is generated by the compiler. So once we get this output, you will always have output.contracts. Then it's the file name of our main contract, which is mytoken.sol, and then it's the contract name. My token, it's like if you open mytoken.sol, this is the contract name that we have here. And then .abi, it gives you the ABI code, so which is the application binary interface, which is required to make function calls. And because we are going to deploy the code at this moment, so the difference between the ABI is the ABI is very much similar to the interface, where it has the function signature, but it doesn't have the actual code which of the function. So the they the ABI has like what parameters function take as an input, what's the function name, what the function returns, but it doesn't know uh, what the function do. It doesn't have the code inside it. So that's why we need the bytecode. And because we want to deploy our smart contract first time, we have to give it all the codes inside the function to the blockchain so that it can store it. So that's why you need the contract bytecode. So the format will always be same, output.contracts, then again your file name, your contract name that you have mentioned here, and then .evm bytecode object. Once you got the bytecode, second thing is we are going to use Web3 APIs. So we have created our own Web3 library, which is at the QRL/Web3. There are, it's still in progress. There are some APIs which are working. There's some of APIs which are still in progress, which might not work. So, but whatever APIs, Web3 APIs we have used in this code, that's going to work. So you should not have any issue using that. So we are going to load our contract using this ABI file. So the Web3 Zond contract requires the ABI as an input. So you have to provide ABI. And because we are going to deploy this contract, it's the first time. So you can use this contract.deploy, this contract object once created. There's a deploy function. Now this deploy function takes two things as an input, data and arguments, where data is the bytecode, which we have got from the compiler by the Solidity compiler, and the argument. So this argument is not necessarily every time, it depends upon your contract. So in my case, my contract has a constructor. So it's a parameterized constructor which takes two input, which is the name of the token and the symbol of this ERC20 token. That's why I have to pass this as an argument, the token name, which is token 123, and the symbol is TOK. So in case your contract doesn't have any parameterized constructor, you don't need to pass any argument. You can remove that. It's totally fine. So once you have done this, the next thing, to deploy it, you have to make a transaction. But for that specific transaction, you need to know the nonce. Okay, so if you are familiar with the blockchain, it's like a nonce is something which has to be unique every time you make the transaction, and it has to be sequential. It starts with zero and it can go beyond like infinite. So we already have an API which gives you the next available nonce. It goes through the blockchain network, Zond blockchain network. It provides the address and it asks for what's the next available nonce, which we can use for our transaction. And then we get this nonce value. It's an integer value, a sequential number. So it's like it should be unique for every transaction. You cannot reuse the nonce which you already have used before. And once you have got the nonce for your address, the next thing is, to deploy this contract, you have to give gas as a fee. And now to get like to know how much gas is required, we have this API estimate gas. So if you call this contract send.estimate gas and you provide your address, it will do like a kind of simulation on the Zond, like Zond API. It will send all the data to the Zond API. Zond API on its side does the simulation, and then it calculates that, okay, this is the required amount of gas which you need, which is the least amount of gas which you need to deploy your contract. So once you get the estimated gas amount, we create the transaction here. So it's like this is how the transaction is created. It's like you provide your address from which your dilithium address from which you are trying to deploy the contract. Then this encoded ABI. So this is basically the data is basically the whole EVM bytecode is included in this. The functions, the code of the functions, everything, the constructor's parameter, everything is passed in this one. And this is automatically done by the Web3 API that we have created. And so we have this nonce, which we already taken from this API, like which is the next nonce available for us for the transaction. Chain ID, it's fixed 0x1, so no need to change that. Even if you change that, it should not create any issue, because right now we are not doing any validation for the chain ID, but there will be validation in future. So just keep it as it is. Estimate gas, which we have taken from the RPC API by the simulation of the contract, how much gas is required for this transaction. And gas price, so basically your transaction fee will be gas price multiplied by the gas, so that will become your transaction fee. So make sure you should have a balance, which is gas multiplied by price. You should have at least that much balance in your dilithium wallet. Otherwise your transaction will fail because of out of gas thing, and your contract will not be deployed. And now this is the value. So value means, the if you are trying to transfer some amount of quanta to your contract, then you can provide this some value here. But note one thing. If you are already familiar with the Solidity, you know this, that you can only transfer funds to a contract if that contract is of payable type. So you have to define a contract as a payable. Otherwise, if you try to send any funds, any quantas to that specific contract which is not payable, it will fail, and it's like you will get back whatever you tried to send to that smart contract. So in our case, our contract is not payable, so the value should be 0, and if you try to add any value here, your contract will not be deployed, it will be failed. So that's why it's 0, and 2 should be blank. So here we are not here we are going to deploy the contract, and at this moment we don't know the contract address. So whenever you are going to deploy the contract, the 2 fields should always remain blank. Then we provide the hex seed, because this is a signed transaction function. It takes the transaction structure and the hex seed. So we have already provided the dilithium hex seed here. So it's what it is going to do is create the transaction, going to sign that, and then you will have this signed transactions in this create transaction structure. So right now we have we haven't added the type yet, so we have to use this small hack here to force to add this type 0x2, but that will be removed in future. So you don't need to play with this, you just keep this as it is, the transaction type 0x2. After this, we call this send sign transaction. So this is the Web3 API, which basically sends your raw transaction to the Zond node, and from there Zond node proceed with this, like validating and processing and getting it added to the block, and then we wait for the receipt. So if you have already worked with Ethereum Web3's API, so basically the receipts are generated once your transaction get processed in the block. So receipts has information like what's your contract address, whether the transaction worked successfully or not, or it failed for some reason, what was the block number in which your transaction was added, and what's the block hash, and other informations, which you can look into documentation if you want to know what other information are provided in this. And then we have confirmation. So it waits for the we have configured it to wait for like 2 confirmations at this moment. So it will show you the number of confirmations. So if you got the receipt, that means your transaction has already been added into the block. After that, if you want to wait for the confirmation, you can, or you can just interrupt the process. At the end of this, we have already written the code which basically generates the contract address locally. So it's like it's not necessary, but it's just for the information, like how the contract address is generated. So it basically takes the dilithium address, basically the address from which you are trying to deploy the contract, and then it takes the nonce that you have used to deploy the contract. Uh, then it just does hashing, keycac 256 hashing at the back end. And after that, whatever hash it gets, it takes the first 20 bytes of it, and that becomes your contract address. So that's too much of technicality, but let's just keep that simple, that you will get the contract address in the receipt. But even then, if you for some reason, if for network issue, if you got disconnected in between, you will still get the contract address here, which is this part of the code. So now we have already updated our hex sheet. So now let's try running this and see how it looks like. So we are going to run our one deploy.js, no warnings. Okay, so this is this. Okay, we got our receipt. This is the receipt. So this is the dilithium address from which we are trying to deploy our contract. Our transaction has already been accepted into the block. Confirmation number 0 means it's just the first block on which your transaction is still uh, I mean, the block has been approved, it's the part of the main chain, your transaction is inside the block, and that's why the confirmation is 0. So as more block will be added to it, you will get like higher confirmations. So it shows the block number on which your transaction has been added. It's 10,499, and the cumulative gas used is 949,965, the gas price. And here we have the from address, the dilithium address from which we deployed this contract. And this address, this is the contract address. So in logs, you get the address, which is the contract address. So make sure you copy this. So I will copy this and keep it handy somewhere.
Kaushal, was that about 30 seconds for a block?
Per block? No, it's 1 minute for a block. But luckily, we made our transaction just before 10 seconds before this first block was going to end. Okay, so all right. So let me note down this here.
Oh, yeah.
So that's our contract address. I have noted it down here for the purpose. Now it's showing you confirmation number one. If you want to interrupt, you can control C interrupt it. Your contract is already deployed. There's no need to wait for two confirmations at this moment. So we have got contract address. We have deployed it from our dilithium wallet, which is having this address. So I also copied this. My dilithium address. This is my dilithium address. So now I will go with off-chain call first. So let me explain you the difference between off-chain and on-chain call. So any call that you would like to make in a smart contract which doesn't require any change in its state. Okay, if there is some function call that you are trying to make, it doesn't require any change in the state. So that doesn't require like you to make any kind of transaction, because you are just going to read some values from whatever is stored in the blockchain. You are not going to make any changes in the state of the contract or anything like that. So in that case, we make the off-chain call. It doesn't require any wallet, it doesn't require any signature, it doesn't require any transaction fee or anything. And so that's the off-chain call. So here we have to update our deployed contract address, contract that we have deployed. So in our case, this is our contract address. We update it here. Okay. And I will again go through with some explanation here. So this get compiler output is same as we discussed in deploy.js, the compiler output, which basically gives you ABI and EVM. Because we have already deployed our contract, the bytecode is already inside the blockchain, so we don't need the bytecode. But because we want to call some of the functions in the contract, so we need the ABI file, ABI code. So we are loading this ABI again, as we have discussed in this one. And once we have this ABI code, we again initialize our contract instance using the Web3 API, where we provide this ABI code and the deployed contract address, which I have already updated here. Once you have this contract instance, you can then call the function which you have written in the contract. So for that, contract dot methods, then balance off. So balance off is it could be either function or a variable. So balance of is a map variable, so it's a public variable. Balance of, that's what we are trying to call at this place. And this map basically takes input, which is an address. uh, so I'm providing it a specific address, and then I'm calling it. We have already discussed about get compiler output in one deploy.js. So here we are getting a compiler output, ABI files, and then we are initializing our contract using Web3 APIs. So we provide ABI file and the deployed contract address. We got this contract instance, and then we are going to call our contract function or variable, whatever it is. So you have to write like contract.methods, and after that, your variable name or the function name. So in our case, we have this balance of as a variable here, which is a map type. So balance of is a map type which takes address as an input and gives you integer as an output, which is the balance. So I'm providing an address, a random address, and then I'm going to call this I'm going to make this off-chain call for my contract with the balance of variable, which, and then I should get the balance of this specific address. So because this is any random address, it should give me a zero balance. So let me open another terminal. This is okay. And it is okay. So if I try to run this, I should get zero balance. Okay, because I have just deployed my contract. So only I have the balance at this moment, and no other wallet address has. But if I check this with my own wallet address, the address that I used to deploy, if I copy this, my dilithium address, paste this here, try to get this, uh, I should get, okay, this is the balance that I have on my own address because I have deployed the contract. So now what we are going to do, we are going to transfer some funds to this wallet address, which doesn't have anything at this moment. So for this, we are going to use onchain call.js, which we already have written, pre-written everything. You just have to make couple of changes to this to make it work. It's like I again have to update the hex seed because this wallet doesn't have any funds and I haven't deployed my contract using this wallet. So onchain call.js, I update my hex seed, and then I have to update my deployed contract address, which I have already copied here. Okay, so now I will explain you what this function works. How does this things work? So it's again the same thing. We are getting the address because we are going to make an on-chain call. So as I mentioned previously, on-chain call, you have to make it when you are trying to change the state. If you are moving some funds, that means it requires the change in the state. So that requires a transaction, that requires the wallet, that requires the fee. So that's what the on-chain call is. It requires the transaction, so fee and everything, because you are going to make some changes in the state of the blockchain of the smart contract or anything. So that's why we go for the on-chain call. If you just want to read values, then off-chain call is something where you doesn't need any fee, any wallet address or anything like that. So we are on-chain call. We are going to move funds to this address, which is 2073A9893. I already have this address here. So, okay, this is the contract address which we have deployed. Again, we have to make the instance of the contract and provided the ABI code. So here's the ABI code, which we are taking from the compiler as already discussed. This is the deployed contract address. The contract address which we have deployed, which is mentioned here. And then because we are going to sign the transaction, we again need to know which is the next nonce available for us to sign this transaction. Otherwise your transaction will fail if you are not using the nonce sequentially, or if you are using a nonce which is already used in the past. So user doesn't have to keep track of the nonce. So that's why we have this API. If you call this web3 API, provide the address, you get the nonce which is available, which you can use in your transaction. Now I'm going to call this contract.methods.transfer. So contract.methods, after this you basically give the function name which you have written in the contract. So we are here going to call the transfer function of our contract, which is written in this file erc20.sol. This is the transfer function. What it does is it removes it's just deduct the balance from the sender and adds the balance to the recipient, whatever recipient you have provided in the parameter, and the amount whatever you have provided in the parameter, and then it emits the event. So in this case, we have already provided the parameter, which is this is the recipient address who will receive the balance, and this is the amount of balance that he's going to receive, 10,000 10,000 of my token. Okay, so that's the ERC20 token which we have deployed. So this gives you basically the data which you require to broadcast. So it's basically kind of EVM thing, EVM bytecode, which has to be sent, which will tell the EVM that, hey, I want to call this contract. This is the sender. Uh, these are the parameters of the contract. This is the function that this is the specific function that I want to call for this for this contract. So all of these things has to be converted into EVM bytecode so that EVM can understand that and process that same information. So that's what we does here. So it creates everything, uh, ABI things and the bytecode, everything whatever you need. And then because we are going to make a transaction, we again need to have the estimated amount of gas is required for this. So again we call this same APIs, which does the simulation at its own side and then comes up with the minimum amount of gas that you need to make this transaction successful. Here we provide the address. So this is the address from which you are going to make the transaction. So I just use the d.get address, which is the dilithium instance, which gives me the dilithium address of my wallet. Once we have this estimated gas, we are again going to use the same format that we used in deploy.js. Sign transaction, the same thing. But in deploy.js, we had this two field blank because we were going to deploy our smart contract and we do not know what's going to be the contract address at that point of time. So it's not required whenever you are going to deploy the smart contract. So that's why the two was empty. But in this case we know that we are going to interact with a specific smart contract because we are going to call a contract function. So of course we know we are going to call the contract function of some contract which is already deployed on the network. So we know the contract address, so we have to provide this deployed contract address into two. Once we have this, then we give this hex seed to sign the transaction. Then this Web3 API just sign the transaction, creates everything inside this. Again, the same hack that we are using at this moment. Do not change this, or you will have the issue. So just keep it as it is. This will be removed in future. And then we broadcast this transaction using the send sign transaction API available in this Web3 package. And then we again wait for the receipt. So as mentioned in this one, just receipt means your transaction has been approved in the block. You will get all the details, what's the block number, if the transaction processed successfully or if there was any issue. So I'm going to run this, and we have already checked before the balance was zero for this address. And so okay, I'm going to run this on-chain call. Okay, so it has sent the transaction and waiting for the receipt. So our block timing is 1 minute, so it may take you around 1 minute or like somewhere around that to get the transactions approved and so the receipt. Okay, transaction has been accepted. We got the receipt. One important thing in this receipt is status. So make sure your status is true. So status true means your transaction is successful. It has been successfully processed. No issues with that. And we have got this. The gas used is 52163. We have got the block hash, block number on which the transaction was added. So now if we check the balance again, we have to make this address. We are transferred to this ECFA. So have this address here. So now if we go to off-chain call.js and check the balance again, we should see the balance 10,000, 10,000, the token that we have transferred. So if I run this, here we see 10,000. So that means our own account should have 10,000 less amount of that token. So if I use my own address, which is this one on this off-chain call.js, I try to run this, it should be less than this, and here it is. Okay. So this is how it works. This is the whole demonstration of the smart contract, how you can deploy it, how you can make off-chain call to check to call any functions if you are not going to play with the state. And this is the on-chain call if you are trying to call any of the smart contract functions which are going to make some state changes, then you are going to use on-chain call.js. So this is everything. In case you get any questions, feel free to ask, or in case you get into any trouble, feel free to ping me on Discord and try my best to help you with the issue. So that's all from my side.